2.1 Explain the importance of security concepts in an enterprise environment. Configuration management. Diagrams such as network diagrams or system architecture diagrams, visually represent the configuration and connectivity of systems and networks. Example, creating a network diagram that illustrates the relationships between servers, switches, routers, and other network devices. Baseline configuration. Baseline configuration defines the standard, secure configuration settings for systems or devices. Example, establishing a baseline configuration document that outlines the approved settings for operating systems, applications, and network devices. Standard naming conventions. Standard naming conventions provide consistency and ease of management by defining a naming structure for systems, devices, or files. Example, using a naming convention that includes location, function, and version information for network devices, such as location_device function_version. Internet Protocol, IP, schema. IP schema refers to the design and allocation of IP addresses and subnets within a network. Example, using a hierarchical IP addressing scheme, such as classless interdomain routing, CIDR, to officially allocate IP addresses and manage network subnets. Data sovereignty. Data sovereignty refers to the concept of data being subject to the laws and regulations of the country or region in which it resides. Example, ensuring that customer data stored in a cloud service complies with the data protection and privacy regulations of the country where the customers reside. Data protection and privacy regulations of the country where the customer. Data loss prevention, DLP. DLP involves implementing technologies and policies to prevent unauthorized disclosure or loss of sensitive data. Example, configuring DLP solutions to monitor and block the transmission of confidential documents via email or file sharing platforms. Masking. Data masking involves replacing sensitive data with fictitious or obfuscated values to protect its confidentiality. Example, masking credit card numbers in a database by replacing all but the last 4 digits with random characters. Encryption. At rest. Encryption at rest involves encrypting data when it is stored or saved on storage devices. Example, using full disk encryption to protect the data stored on a laptop's hard drive. In transit/motion, encryption in transit or motion involves securing data as it is transmitted over networks or communication channels. Example, implementing transport layer security, TLS, or secure sockets layer, SSL, encryption for secure web communication. In processing, encryption in processing involves encrypting sensitive data while it is being processed or used within applications or systems. Example, using cryptographic algorithms to encrypt and protect sensitive data during its processing within a financial transaction system. Tokenization. Tokenization replaces sensitive data with unique tokens, reducing the exposure of actual data during processing or storage. Example, replacing credit card numbers with randomly generated tokens for payment processing, with the actual card numbers stored securely in a token vault. Rights management. Rights management involves controlling access and usage rights for sensitive data. Example, implementing digital rights management, DRM, solutions to restrict unauthorized copying or distribution of copyrighted materials. Geographical considerations. Geographical considerations involve understanding and addressing security risks and regulations specific to different regions or countries. Example, complying with data residency requirements that mandate customer data to be stored within a specific country or region. Response and recovery controls. Response and recovery controls include incident response plans, backup and restoration procedures, and disaster recovery strategies. Example, developing an incident response plan that outlines the steps to be taken during a security incident, including containment, eradication, and recovery. Secure Sockets Layer (SSL/Transport Layer Security) TLS inspection. SSL/TLS inspection involves inspecting encrypted network traffic to detect and prevent malicious activities. Example: implementing a security appliance that decrypts SSL/TLS traffic, inspects the content for threats, and re-encrypts it before forwarding it to its destination. Hashing involves transforming data into a fixed-length string of characters, typically for verifying data integrity or password storage. Example: calculating a hash value for a downloaded file and comparing it with the provided hash value to ensure the file has not been tampered with. API considerations. API considerations involve securing application programming interfaces, APIs, to prevent unauthorized access or abuse. Example: implementing authentication and authorization mechanisms, such as OAuth or API keys, to control access to APIs and protect sensitive data. Site resiliency. Hotsite. A hotsite is a fully operational backup site with up-to-date infrastructure and data, ready to take over in case of a primary site failure. Example: replicating critical systems and data in real time to a geographically separate hotsite to ensure minimal downtime. Cold site. A cold site is a backup site that lacks the necessary infrastructure and data, requiring manual setup and configuration in the event of a primary site failure. Example: leasing an empty office space with power and network connectivity to serve as a cold site, requiring hardware installation and data restoration during a disaster. Warm site. A warm site is a backup site with partially configured infrastructure and preloaded data, requiring some setup and configuration before becoming fully operational. Example: maintaining a secondary data center with partially configured servers and regular data backups, requiring minimal setup time during a disaster. Deception and disruption. Honeypots. Honeypots are decoy systems or networks designed to attract attackers, allowing security teams to study their techniques and gather intelligence. Example: deploying a server with intentionally vulnerable software to attract and monitor attackers attempting to exploit it. Honeyfiles. Honeyfiles are decoy files placed in strategic locations to lure attackers and alert security teams of unauthorized access or data breaches. Example: planting a document named confidential_financial_data.xlsx on a server with unique tracking capabilities to detect unauthorized access attempts. Honeynets. Honeynets are complete, isolated networks designed to attract and trap attackers, enabling detailed analysis of their activities and methods. Example: setting up a honeynet with simulated systems and services to gather information about attacker behaviors and techniques. Fake telemetry. Fake telemetry involves generating and sending fake or decoy system data or network traffic to deceive and confuse attackers. Example: sending false network traffic statistics to an attacker attempting to map the network, making it difficult for them to distinguish real from fake information. DNS sinkholing, also known as DNS blackholing, involves redirecting malicious or unwanted DNS traffic to a sinkhole server instead of the intended destination. This technique is used to block access to malicious domains, prevent malware infections, or gather threat intelligence. Example: setting up a DNS sinkhole server that intercepts DNS requests for known malicious domains and responds with a non-existent or benign IP address, effectively blocking the communication with the malicious servers. 2.2 Summarize virtualization and cloud computing concepts. Cloud models. Infrastructure as a Service (IaaS) provides virtualized computing resources such as virtual machines, storage, and networks as a service. Example, using Amazon Web Services, AWS, Elastic Compute Cloud, EC2, to provision virtual servers and storage for hosting applications. Platform as a Service, PaaS offers a platform for developing, testing, and deploying applications, including operating systems, development frameworks, and runtime environments. Example, using Microsoft Azure App Service to develop and deploy web applications without managing the underlying infrastructure. Software as a Service, SaaS delivers software applications over the Internet, eliminating the need for local installation and maintenance. Example, using Google Workspace, formerly G Suite, for cloud-based email, collaboration, and productivity tools. Anything as a Service, XaaS represents the delivery of any IT-related service over the Internet. It includes services beyond IaaS, PaaS, and SaaS. Example, Database as a Service, DBaaS, provides managed database services, such as Amazon RDS or Microsoft Azure SQL Database. Public cloud services are available to the general public and are owned and operated by third-party cloud providers. Example, Amazon Web Services, AWS, Microsoft Azure, or Google Cloud Platform, GCP. Community cloud services are shared by several organizations with common interests, such as security or compliance requirements. Example, a cloud infrastructure shared by multiple financial institutions for secure transaction processing. Private cloud services are dedicated to a single organization and may be hosted on premises or by a third-party provider. Example, a private cloud deployed within an organization's data center for exclusive use by its employees and partners. Hybrid cloud combines public and private cloud environments, allowing data and applications to be shared between them. Example, using a combination of on-premises servers and public cloud services to host and manage a company's IT infrastructure. Cloud service providers. Cloud service providers are organizations that offer cloud-based services and infrastructure to customers. Example, Amazon Web Services, AWS, Microsoft Azure, or Google Cloud Platform, GCP. Managed Service Provider, MSP/Managed Security Service Provider, MSSP. MSPs/MSSPs are companies that provide managed services, including cloud management and security services, to organizations. Example, a managed service provider offering 24/7 monitoring, patch management, and incident response for a company's cloud infrastructure. On-premises versus off-premises. On-premises refers to infrastructure or services hosted within an organization's own physical premises, while off-premises refers to infrastructure or services hosted outside the organization's premises, such as in a cloud environment or a data center. Example, hosting a web server on physical servers within an organization's own data center, on-premises, versus hosting the web server on virtual machines in a public cloud environment, off-premises. Fog computing. Fog computing extends cloud computing capabilities to the edge of the network, closer to the data source or end users, enabling faster processing and reducing latency. Example, deploying edge devices or gateways that perform local data processing and analytics in a smart city environment. Edge computing. Edge computing involves processing and analyzing data at or near the edge devices or sensors, reducing the need for data transmission to the cloud or data center. Example, running machine learning algorithms on IoT devices to perform real-time analysis of sensor data without relying on cloud resources. Thin client. A thin client is a lightweight computer or device that relies on a central server or cloud infrastructure for processing and storage. Example, using a thin client device to access virtual desktops hosted on a central server or cloud-based virtual desktop infrastructure, VDI. Containers. Containers provide lightweight, isolated environments for running applications and their dependencies, enabling efficient application deployment and scalability. Example, using Docker containers to package and deploy microservices-based applications in a cloud environment. Microservices/API. Microservices architecture involves breaking down applications into smaller, loosely coupled services that can be developed, deployed, and scaled independently. Application programming interfaces, APIs, enable communication between these microservices. Example, building a cloud-based e-commerce platform using microservices for catalog management, order processing, and payment integration, with APIs facilitating communication between the services. Infrastructure as code. Infrastructure as code, IAC, is the practice of managing and provisioning infrastructure resources using machine-readable configuration files, automating the deployment and management processes. Example, using tools like Terraform or Ansible to define infrastructure configurations and automatically provision cloud resources based on code-defined templates. Software-defined networking, SDN separates the control plane from the data plane in networking, allowing for centralized management and programmability of network resources. Example, implementing SDN to dynamically configure network switches and routers based on application needs and traffic patterns. Software-defined visibility, SDV enables granular monitoring and visibility into network traffic by capturing and analyzing data flows at the software level. Example, using SDV tools to monitor and analyze network traffic for detecting anomalies, intrusions, or performance issues. Serverless architecture. Serverless architecture allows developers to focus on writing code without managing underlying servers. It involves using cloud functions or serverless platforms to execute application logic. Example, building a serverless web application using AWS Lambda functions to process user requests and trigger actions without provisioning or managing servers. Services integration. Services integration involves connecting and orchestrating multiple cloud services or microservices to enable seamless communication and collaboration. Example, integrating a cloud-based CRM system with an email marketing service to automatically synchronize customer data and send targeted email campaigns. Resource policies. Resource policies define access controls and permissions for cloud resources, ensuring secure and controlled access. Example, creating an AWS Identity and Access Management (IAM) policy to grant specific permissions to users or groups for managing EC2 instances. Transit Gateway. Transit Gateway is a network transit hub that simplifies network connectivity and routing between multiple virtual private clouds, VPCs, or on-premises networks. Example, using AWS Transit Gateway to establish secure and scalable communication between VPCs in different regions. Virtualization. Virtualization involves creating virtual versions of physical resources, such as servers or storage, to improve resource utilization and flexibility. Example, using hypervisor technology, like VMware or Hyper-V, to run multiple virtual machines, VMs, on a single physical server. Virtual machine, VM, sprawl avoidance. VM sprawl avoidance refers to controlling the proliferation of unmanaged and unused VMs to prevent resource wastage and security risks. Example, implementing VM lifecycle management policies to track and retire unused VMs automatically. VM escape protection. VM escape protection involves securing the hypervisor and host environment to prevent unauthorized access or exploitation of vulnerabilities that could allow attackers to escape from a VM and access the underlying host or other VMs. Example, applying security patches and hardening configurations to the hypervisor and regularly auditing for potential vulnerabilities. 2.3 Summarized secure application development, deployment, and automation concepts. Environment. Development. The development environment is where software applications are created, modified, and tested before being deployed to production. Example, developers working on coding and testing new features or functionalities in a development environment. Test. The test environment is used to perform thorough testing of software applications to identify bugs, vulnerabilities, or compatibility issues. Example, QA testers running test cases and conducting various testing techniques in a controlled test environment. Staging. The staging environment is a replica of the production environment and is used for final testing and validation before deploying new applications or updates to the production environment. Example, verifying the performance and functionality of an application in a staging environment that closely mimics the production environment. Production. The production environment is the live or operational environment where the application is accessed by end users. Example, the actual server or cloud infrastructure where the application is deployed and accessed by customers or clients. Quality assurance, QA. The QA environment is used to perform quality assurance activities, such as testing, verification, and validation, to ensure that software meets quality standards. Example, running automated test scripts and performing manual testing in a QA environment to identify any functional or security issues. Provisioning and deprovisioning. Provisioning refers to the process of setting up and configuring resources, such as servers or virtual machines, to make them available for use. Deprovisioning, on the other hand, involves removing or disabling resources when they are no longer needed. Example, automatically provisioning a virtual machine in a cloud environment when a new user or application request is received, and deprovisioning it when the user or application is no longer active. Integrity measurement. Integrity measurement involves verifying the integrity of files, configurations, or software components to ensure that they have not been tampered with or modified. Example, calculating a hash value for a file and comparing it with the stored hash value to check if the file has been modified or tampered with. Secure coding techniques. Secure coding techniques involve implementing coding practices that enhance the security of software applications. Examples of secure coding techniques include normalization, ensuring that input data is properly validated, sanitized, and transformed to prevent injection attacks such as SQL injection or cross-site scripting, XSS. Stored procedures, utilizing stored procedures for database interactions to prevent SQL injection attacks and enforce data access controls. Obfuscation/camouflage, applying techniques to obscure or make code difficult to understand for potential attackers, such as renaming variables or using code obfuscation tools. Code reuse/dead code, avoiding code reuse of deprecated or unused code that may introduce security vulnerabilities. Server-side versus client-side execution and validation, ensuring that sensitive operations and input validations are performed on the server side to prevent manipulation by malicious clients. Memory management, properly managing memory to prevent vulnerabilities such as buffer overflows or memory leaks. Use of third-party libraries and SDKs, selecting and using trusted and up-to-date third-party libraries and software development kits, SDKs, to avoid vulnerabilities introduced by insecure or outdated components. Data exposure, implementing data protection mechanisms such as encryption or access controls, to prevent unauthorized access or exposure of sensitive data. Open Web Application Security Project, OWASP. OWASP is an open community that focuses on improving the security of software applications. It provides resources, best practices, and guidelines for secure application development. Example, referring to the OWASP Top 10 list of the most critical web application security risks and implementing appropriate controls to mitigate those risks. Software diversity. Software diversity involves using different software or compilers to build applications to reduce the impact of common vulnerabilities or attacks. Example, using multiple compilers or different programming languages to compile different components of an application to reduce the likelihood of widespread vulnerabilities. Automation/scripting. Automation and scripting involve using scripts or automated processes to streamline tasks and improve efficiency. Examples include automated courses of action, creating scripts or automation workflows to perform predefined actions in response to specific events or incidents. Continuous monitoring, implementing automated monitoring tools and processes to continuously monitor the security posture of systems and networks. Continuous validation, automating security testing and validation processes, such as vulnerability scanning or penetration testing, on a regular basis. Continuous integration, using automated tools and processes to integrate code changes from multiple developers into a shared repository, allowing for early detection of code conflicts or vulnerabilities. Continuous delivery, automating the deployment of software applications to various environments, ensuring consistent and reliable delivery. Continuous deployment, automating the deployment of software applications to the production environment, reducing manual intervention and improving deployment speed. Elasticity. Elasticity refers to the ability of a system to dynamically scale resources up or down based on demand. Example, autoscaling a cloud-based application to add more resources during peak periods and reduce resources during periods of low usage. Scalability. Scalability refers to the ability of a system or application to handle increased workloads and growing user demands. Example, designing a web application to scale horizontally by adding more servers to distribute the workload as the user base expands. Version control. Version control involves managing and tracking changes to software code or configuration files, enabling collaboration and tracking of different versions. Example, using Git or Subversion for version control, allowing multiple developers to work on the same codebase and maintain a history of changes. 2.4 Summarize authentication and authorization design concepts. Authentication methods. Directory services. Directory services, such as Microsoft Active Directory or LDAP, provide centralized authentication and authorization services for users and devices within a network. Example, using Active Directory to authenticate users and manage access to network resources. Federation. Federation enables single sign-on (SSO) across multiple systems or domains by establishing trust relationships between identity providers and service providers. Example, implementing Security Assertion Markup Language (SAML) to enable SSO between an organization's internal systems and external cloud-based services. Attestation. Attestation involves verifying the integrity and authenticity of a system's hardware or software components before allowing access or executing critical operations. Example, using a Trusted Platform Module (TPM) to provide hardware-based attestation and measurement of a system's integrity. Technologies. Time-based one-time password, TOTP. TOTP generates one-time passwords that are valid for a short period, usually based on a time synchronization algorithm. Example, using Google Authenticator or Microsoft Authenticator to generate time-based one-time passwords for two-factor authentication. HMAC-based one-time password, HOTP. HOTP generates one-time passwords based on a counter, increasing the password with each authentication attempt. Example, using a YubiKey device to generate HMAC-based one-time passwords for multi-factor authentication. Short Message Service, SMS-based authentication sends one-time passwords for verification codes to the user's mobile device via text messages. Example, receiving a verification code via SMS to complete the authentication process for an online banking transaction. Token key authentication involves using physical tokens, such as hardware security tokens or smart cards, to generate authentication credentials. Example, inserting a smart card into a card reader and entering a PIN to authenticate and access a secure system. Static codes are pre-generated, fixed passwords or codes used for authentication. Example, using a printed list of backup codes as an alternative authentication method in case of device loss or failure. Authentication applications installed on mobile devices generate one-time passwords or provide push notifications for user authentication. Example, using the Microsoft Authenticator app to receive push notifications for approving login requests. Push notifications. Push notification-based authentication sends an authentication request to a mobile device, prompting the user to approve or deny the login attempt. Example, receiving a push notification on a mobile device to authorize access to an application or system. Phone call-based authentication involves receiving an automated phone call to verify the user's identity or approve access. Example, answering an automated phone call and entering a verification code to authenticate and access a secure system. Smart card authentication. Smart card authentication requires users to insert a physical smart card into a card reader, along with entering a PIN, for authentication. Example, using a smart card with a digital certificate to authenticate and access a secure building or network. Biometrics. Biometrics involves using unique physical or behavioral characteristics for authentication. Examples of biometric authentication include fingerprint, scanning and matching fingerprints for authentication. Retina, analyzing the patterns of blood vessels at the back of the eye for authentication. Iris, capturing and comparing the unique patterns in the iris of the eye for authentication. Facial, analyzing facial features or patterns for authentication. Voice, analyzing the unique characteristics of a person's voice for authentication. Vein, scanning and matching patterns of veins under the skin, typically in the hand or finger, for authentication. Gait analysis, analyzing a person's walking pattern or style for authentication. Efficacy rates. Efficacy rates measure the accuracy and effectiveness of biometric authentication systems in correctly identifying individuals. False acceptance. False acceptance occurs when an unauthorized person is incorrectly granted access. False rejection. False rejection occurs when an authorized person is incorrectly denied access. Crossover error rate. The crossover error rate represents the point at which the false acceptance rate and false rejection rate are equal, indicating the balance between security and convenience. Multi-factor authentication, MFA, factors and attributes. Factors. MFA involves combining multiple factors for authentication, such as something you know, passwords, PINs, or security questions. Something you have, physical tokens, smart cards, or mobile devices. Something you are, biometrics, such as fingerprints or iris scans. Attributes. MFA may also consider additional attributes for authentication. Somewhere you are, location-based factors, such as geolocation or IP address. Something you can do, behavioral factors, such as typing patterns or voice recognition. Something you exhibit, behavioral factors, such as gestures or handwriting. Someone you know, knowledge-based factors, such as personal relationships or shared secrets. Authentication, authorization, and accounting, AAA. AAA refers to the processes and technologies involved in verifying identities, authentication, granting access privileges, authorization, and tracking user activities, accounting. Example, Radius, Remote Authentication Dial-In User Service, is a commonly used AAA protocol for authenticating and authorizing remote users. Cloud versus on-premises requirements. Cloud and on-premises environments have different requirements and considerations for authentication. Examples include cloud, ensuring secure and reliable authentication protocols, strong encryption, and secure management of user credentials in a cloud environment. On-premises, implementing secure authentication mechanisms such as strong password policies, two-factor authentication, and secure directory services for on-premises systems and networks. 2.5 Given a scenario, implements cybersecurity resilience. Redundancy. Geographic dispersal. Geographic dispersal involves distributing resources across different physical locations to ensure availability in the event of a localized incident. Example, replicating data and services across multiple data centers in different regions or countries. Disk redundancy. Disk redundancy involves using redundant storage configurations to protect against data loss. Example, implementing RAID, redundant array of inexpensive disks, levels such as RAID 1, mirroring, or RAID 5, striping with parity, for fault tolerance. Multipath refers to the use of multiple network paths between systems for increased redundancy and fault tolerance. Example, configuring servers with multiple network interface cards, NICs, to establish multiple paths for network communication. Network redundancy ensures network availability by implementing redundant network components or paths. Example, deploying redundant routers, switches, or links to prevent single points of failure in the network infrastructure. Load balancers. Load balancers distribute incoming network traffic across multiple servers to improve performance and availability. Example, using a load balancer to evenly distribute web traffic across multiple web servers in a web application infrastructure. NIC teaming. NIC teaming, also known as link aggregation or bonding, combines multiple network interfaces to create a single logical network connection for redundancy and increased bandwidth. Example, combining multiple NICs on a server to create a single high bandwidth and fault-tolerant network connection. Power redundancy ensures continuous power supply to critical systems. Example, implementing redundant power sources such as uninterruptible power supplies, UPS, generators, or dual power supplies for servers. Managed Power Distribution Units, PDUs. Managed PDUs provide control and monitoring capabilities for power distribution, enabling efficient power management and redundancy. Example, using managed PDUs to monitor power usage, control power distribution remotely, and ensure redundancy in power supply. Replication. Storage Area Network, SAN, replication. SAN replication involves replicating data between storage systems over a high-speed network for data protection and disaster recovery. Example, using SAN replication to mirror data between primary and secondary storage systems for continuous data availability. Virtual machine, VM, replication. VM replication involves replicating VMs from one host to another for high availability and disaster recovery. Example, configuring VM replication between primary and secondary data centers to ensure VM availability in the event of a system or site failure. On-premises versus cloud. On-premises On-premises refers to having systems and resources located within an organization's physical premises or data centers. Example, hosting servers and storage infrastructure in an organization's own data center for direct control and management. Cloud refers to utilizing remote servers and services provided by a cloud service provider over the Internet. Example, deploying applications or storing data in a public cloud platform such as Amazon Web Services, AWS, or Microsoft Azure. Backup types. Full backup. A full backup copies all data from a source to a backup location. Example, creating a full backup of a server's data and configurations to a backup device or cloud storage. Incremental backup. An incremental backup only copies the changes made since the last backup, reducing backup time and storage requirements. Example, performing an incremental backup of files modified or created since the last backup was performed. Snapshot backup. A snapshot backup captures the current state of a system or data at a specific point in time. Example, taking a snapshot backup of a virtual machine to capture its current configuration, state, and data. Differential backup. A differential backup copies the changes made since the last full backup, providing a more recent backup than incremental backups. Example, performing a differential backup of files modified since the last full backup. Tape backup. Tape backup involves storing data on magnetic tape cartridges for long-term storage and archiving. Example, using tape drives or tape libraries to create backups and store data offline for disaster recovery purposes. Disk backup. Disk backup utilizes hard disk drives or solid-state drives as backup storage. Example, using external hard drives or network-attached storage (NAS) devices to perform backups. Copy backup. A copy backup creates an identical copy of data without marking it as a backup. Example, creating a copy of important files on a separate storage device or location for redundancy. Network-attached storage (NAS) backup. NAS backup involves using a dedicated network storage device for backup and restore operations. Example, backing up critical data to a NAS device connected to the network. Storage area network (SAN) backup. SAN backup involves utilizing a high-speed network infrastructure to perform backups of data stored on a SAN. Example, backing up data from SAN storage arrays to a separate backup SAN. Cloud backup. Cloud backup stores data in a remote cloud environment, providing off-site storage and disaster recovery capabilities. Example, using a cloud backup service to securely store data in the cloud and restore it when needed. Image backup. An image backup creates a complete copy of a system or disk, including the operating system, applications, and data. Example, taking an image backup of a server or workstation to enable full system recovery in case of a system failure. Online versus offline backup. Online backup involves backing up data while the system or service is running, ensuring continuous data protection. Offline backup requires the system or service to be stopped or taken offline during the backup process. Example, performing an online backup of a database while it is actively serving requests. Offsite storage. Offsite storage involves storing backup data at a location separate from the primary data or systems to protect against site-wide disasters. Example, sending backup tapes or utilizing cloud-based backup services to store data offsite. Distance considerations. Consideration of geographical distance between primary and backup locations to ensure adequate protection against regional disasters or disruptions. Example, implementing off-site backup storage at a geographically distant location to mitigate the risk of a single disaster affecting both primary and backup sites. Non-persistence. Revert to known state. Non-persistence involves reverting systems or virtual environments to a known good state to eliminate any modifications or potential compromises. Example, using virtualization technology to revert a virtual machine to its original snapshot after each use. Last known good configuration, restoring systems to the last known good configuration, which was previously validated and known to be free from issues or compromises. Example, restoring a system to a previous backup or configuration state that was verified to be secure and functional. Live boot media, booting a system or device using external media, such as a CD or USB drive, to ensure a clean and controlled environment. Example, booting a compromised system from a read-only live CD or USB drive to perform security scans or recover data without executing any potentially malicious code. High availability. High availability involves designing systems or infrastructure to minimize downtime and ensure continuous operation. Example, implementing redundant servers, load balancing, and failover mechanisms to provide uninterrupted access to critical services. Scalability involves the ability of a system or application to handle increased workloads and growing demands by expanding its resources. Example, adding additional servers or increasing computing power to accommodate increased user traffic or data processing requirements. Restoration order determines the sequence in which systems or services should be restored during disaster recovery scenarios. Example, establishing a restoration order that prioritizes critical systems, databases, or infrastructure components to minimize downtime and restore essential services first. Diversity. Technologies, implementing diverse technologies or solutions from different vendors to avoid single points of failure or vulnerabilities shared by similar technologies. Example, deploying firewalls and intrusion detection systems from different vendors to provide diverse security measures. Vendors, utilizing multiple vendors for products or services to mitigate the risks associated with relying on a single vendor. Example, using different vendors for cloud services, network equipment, or antivirus solutions. Crypto, implementing cryptographic algorithms or solutions from different providers to ensure diverse encryption and protection mechanisms. Example, using different encryption algorithms or libraries for different purposes, such as AES for data encryption and RSA for digital signatures. Controls, implementing diverse security controls such as access controls, monitoring systems, or authentication methods to provide layered defense and reduce the impact of a single control failure. Example, implementing both network-based and host-based intrusion detection systems for comprehensive threat monitoring. 2.6 Explain the security implications of embedded and specialized systems. Embedded systems. Raspberry Pi, a low-cost, credit card-sized computer that plugs into a computer monitor or TV, and uses a standard keyboard and mouse. Used in a wide array of digital projects. Example, you can create a Raspberry Pi-powered home security system with cameras that alerts you whenever an intruder is detected. Field Programmable Gate Array, FPGA, an integrated circuit designed to be configured by the customer or designer after manufacturing. They're generally used for specific applications or specific tasks. Example, an FPGA could be used in image processing applications, such as edge detection in photos. Arduino, open source electronics platform based on easy-to-use hardware and software. Arduino boards read inputs and turn it into an output. Example, an Arduino board can read the output from a temperature sensor and control a fan based on the temperature reading. SCADA/ICS systems, these are large-scale processes that can include multiple sites and large distances. They are often used in industries such as facilities, industrial, manufacturing, energy, and logistics. Example, an oil refinery may use SCADA systems to monitor and control the refining processes across multiple sites. Internet of Things, IoT. IoT devices include sensors, smart devices, wearables, and facility automation devices. They often come with weak default settings that can pose security risks. Example, a smart thermostat in a home that is connected to the internet and can be controlled remotely. This device could have weak default passwords that hackers can exploit to gain control of the device. Specialized systems, these include medical systems, vehicles, aircraft, and smart meters. These systems often have unique security considerations. Example, a connected car that includes a vehicle management system communicating with a central server for updates and diagnostics. It can be a target for hackers to take control over the vehicle. Voice over IP, VoIP, a method for taking analog audio signals, like the kind you hear when you talk on the phone, and turning them into digital data that can be transmitted over the internet. Example, services like Skype or Zoom use VoIP to enable calls over the internet. HVAC systems. HVAC systems control the heating, ventilation, and air conditioning in buildings. They're often connected to a network for remote monitoring and control, making them potential targets for cyber attacks. Example, an attacker might compromise a building's HVAC system to disrupt its operations or to gain unauthorized access to the building's network. Drones, unmanned aerial vehicles that can be remotely controlled or fly autonomously. They can pose a security risk if they are used for surveillance or if they're hacked. Example, a hacker might take over a commercial drone to spy on a corporate facility. Multifunction printer, MFP, a printer that serves several functions, including printing, scanning, and faxing. If connected to a network, it can pose a security risk. Example, an attacker could exploit weak security settings on a networked printer to gain access to sensitive documents. Real-time operating system, RTOS, an operating system that processes data as it comes in, typically used in systems requiring immediate response. Example, RTOS is often used in embedded systems in cars or planes, where immediate processing is crucial. HVAC systems. HVAC systems control the heating, ventilation, and air conditioning in buildings. They're often connected to a network for remote monitoring and control, making them potential targets for cyber attacks. Example, an attacker might compromise a building's HVAC system to disrupt its operations or to gain unauthorized access to the building's network. Surveillance systems includes devices like security cameras and recording systems. These can be hacked to conduct surveillance or disrupt the system. Example, a hacker could disable a security camera system to prevent detection during a physical intrusion. System on chip, SoC, an integrated circuit that contains all the necessary hardware and software for a complete system. Example, an SoC in a smartphone might include the CPU, GPU, memory, and other components. Communication considerations. Technologies include 5G, narrowband, baseband radio, SIM cards, and Zigbee. Each has unique security considerations. Example, 5G networks have greater speed and capacity, but may also have new security vulnerabilities compared to older networks. Constraints. Constraints on security can include power, compute, network, crypto, inability to patch, authentication, range, cost, and implied trust. Each constraint presents different security challenges and vulnerabilities. Example, IoT devices often run on low power and have limited computing capacity, making it hard to run complex encryption algorithms for secure communication. 2.7 Explain the importance of physical security controls. Bollards/barricades, physical security measures designed to prevent unauthorized or forceful vehicle entry into a secured area. Example, use of bollards around a government building to prevent a vehicle from crashing into the structure. Access control vestibules, these are small rooms with two sets of interlocking doors such that the first set of doors must close before the second set opens. They prevent tailgating and piggybacking. Example, secure facilities or data centers often use these to prevent unauthorized access. Badges identification tool used to authenticate personnel. Example, an employee badge with a magnetic stripe used for access to a secure building. Alarms systems designed to alert of potential threats or breaches. Example, an alarm system that triggers when an unauthorized access attempt is made. Signage, visible indicators or instructions related to security measures and policies. Example, a sign warning of video surveillance in the area. Cameras, key components of surveillance systems, may have capabilities like motion recognition and object detection. Example, a camera with motion recognition that starts recording when movement is detected. Closed-circuit television, CCTV, a system of cameras and monitors used for surveillance. Example, a CCTV system in a retail store used to deter and identify thieves. Industrial camouflage techniques used to hide or disguise certain assets or infrastructure. Example, a cell tower designed to look like a tree. Personnel, people involved in security operations, such as guards, robot sentries, and receptionists. Two-person integrity/control is a system where two authorized individuals are needed to perform a certain task. Example, nuclear facilities often require two authorized individuals to initiate critical procedures. Locks, physical, electronic, and biometric locks provide security by restricting access. Cable locks are often used for portable equipment. Example, biometric locks use fingerprints or retinal scans to allow access. USB data blocker, a device that allows charging but blocks data pins, preventing data transfer. Example, use a USB data blocker when charging a device at a public charging station to prevent data theft or malware injection. Lighting, adequate illumination can deter criminal activity and enhance surveillance effectiveness. Example, adequate exterior lighting around a warehouse can deter potential intruders. Fencing, physical barriers to control access. Example, a high-security fence around a power plant. Fire suppression systems designed to detect and extinguish fires. Example, a sprinkler system in an office building. Sensors, devices used to detect changes in environment such as motion, noise, proximity, moisture, or temperature changes. Example, a motion sensor that triggers an alarm when movement is detected in a secured area after hours. Drones, unmanned aircrafts often used for surveillance. Example, a drone used to monitor a large outdoor event for security threats. Visitor logs, records of individuals who enter and exit a facility. Example, a logbook at a corporate office reception where visitors sign in and out. Faraday cages, structures that block electromagnetic fields, protecting electronic equipment from static and non-static electric fields. Example, a Faraday cage in a laboratory to protect sensitive equipment from external electromagnetic interference. Air gap, a security measure to ensure that a secure network is physically isolated from unsecured networks. Example, sensitive military networks often use an air gap to prevent cyber attacks. Screen subnet, previously known as demilitarized zone, a separate network located outside the organization's firewall used to provide access to an external service without exposing the internal network. Example, a company may host its public website on a server in the DMZ, separate from its internal network. Protected cable distribution security measure to protect network cabling from interception or damage. Example, network cables can be run in protective conduits to prevent tampering. Secure areas, physically secure environments where sensitive information is processed or stored. These include air-gap systems, vaults, safes, hot aisles, and cold aisles. Example, a data center will have hot aisles and cold aisles to manage the cooling of servers. Secure data destruction, ensuring that data is completely erased and unrecoverable. Methods include burning, shredding, pulping, pulverizing, degaussing, and third-party solutions. Example, a company might use a third-party solution to securely erase hard drives before disposal. 2.8 Summarize the basics of cryptographic concepts. Digital signatures provides authentication, integrity, and non-repudiation. Example, when you sign a digital document with your private key, anyone can verify your signature, authenticity, using your public key. Key length, the size of a key used in a cryptographic algorithm. The larger the key, the harder it is to crack. Example, AES-256 has a key length of 256 bits, making it more secure than AES-128, which has a key length of 128 bits. Key stretching, a method used to make brute force attacks more difficult by increasing the time it takes to test each possible key. Example, PBKDF2 and BCRYPT are key stretching algorithms. Salting, random data added to a password before hashing it to make it more resistant to rainbow table attacks. Example, storing passwords as a hash of the password and a unique salt, rather than just the hash of the password. Hashing, a function that converts an input into a fixed-size string of bytes. It is used to check data integrity. Example, using SHA-256 to hash a file and then sharing the hash value with the recipient for verification. Key exchange, a method by which cryptographic keys are exchanged between parties. Example, the Diffie-Hellman protocol allows two parties to generate a shared secret key for communication. Elliptic curve cryptography, a type of public key cryptography based on the algebraic structure of elliptic curves. Example, ECC is often used in SSL/TLS for secure web browsing. Perfect forward secrecy, a property of secure communication protocols where compromise of long-term keys does not compromise past session keys. Example, using ephemeral Diffie-Hellman keys for each TLS session. Quantum, the principles of quantum mechanics applied to computing and communications, presenting new challenges and opportunities for cryptography. Example, quantum key distribution for secure communication. Post-quantum cryptography that is thought to be secure against attack by quantum computers. Example, lattice-based cryptography. Ephemeral, temporary, or short-lived cryptographic keys. Example, ephemeral keys are used in perfect forward secrecy. Modes of operation, the procedures used for applying a cryptographic algorithm to data. Example, cipher block chaining, CBC, and counter, CTR, are modes of operation for block ciphers. Blockchain, a decentralized and distributed digital ledger. Example, Bitcoin is based on blockchain technology. Cipher suites, a set of cryptographic algorithms used together to secure a network connection. Example, an example of a cipher suite might be TLS_AES_256_GCM_SHA-384, which specifies TLS 1.3 with AES 256-bit GCM encryption and SHA-384 for the hash. Symmetric versus asymmetric. Symmetric encryption uses the same key for encryption and decryption. Asymmetric encryption uses different keys, public key for encryption and private key for decryption. Example, AES is a symmetric encryption algorithm. RSA is an asymmetric encryption algorithm. Lightweight cryptography, cryptographic algorithms designed for environments where resources are limited. Example, present is a lightweight symmetric block cipher. Steganography, the practice of hiding data within other data. Example, hiding a secret message within an image file. Homomorphic encryption, a form of encryption that allows computations to be performed on ciphertext and generate an encrypted result which, when decrypted, matches the result of operations performed on the plaintext. Example, performing computations on encrypted data in cloud storage without having to decrypt it first. Common use cases. Different cryptographic techniques are better suited to different use cases, including low-power devices, low latency, high resiliency, supporting confidentiality, supporting integrity, supporting obfuscation, supporting authentication, and supporting non-repudiation. Example, using lightweight cryptography for IoT devices, low power. Limitations. There are trade-offs and limitations to all cryptographic systems, including speed, size, weak keys, time, longevity, predictability, reuse, entropy, computational overheads, and resource versus security constraints. Example, symmetric encryption is faster than asymmetric, but asymmetric provides a solution for the key distribution problem.